Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Yeah, welcome everyone for this talk today. It's Riccardo Senica talking from the University of Milan. He's a professor there and holds a chair in machine learning, and his current research interests lie at the intersection of statistical physics, computer science, and AI. And Riccardo is an Alice Fellow and member of the Alice Unit Milano, and as well director of the Alice program Quantum and Physics-Based Machine Learning. And today's talk is about low-energy learning from the analysis of learning landscapes in deep and recurrent neural networks. Riccardo, the floor is yours.
So good afternoon to everybody. It's a pleasure to give this talk. Just a few words about the topic. This will not be a talk about applications to solve very important problems of sustainability, but it's more about the sustainability of AI itself. So how can we make it more energy efficient and hopefully reduce the cost of implementing AI tools. And so I would like to give my contribution in this direction and give some theoretical or modeling, say, results in this respect that I think in the not so far future can lead to more sustainable technologies. I think I can start directly. So the plan of the talk more or less is the following. First, I want to give a few generic comments about, say, what I call the metabolism of AI, namely how much it costs to perform learning and to use current AI models. Then I would like to compare this with the metabolism of, say, computational neuroscience models and neuromorphic models, and argue that, in fact, they are much more efficient. However, they do not give, say, comparable performance. And then I would like to enter in, say, the scientific aspect of my talk. And first, I want to start with a generic vision of the field. So first of all, how is it possible that the algorithm that we use for learning can actually work, in the sense that the system we want to train are incredibly complex, and yet we use algorithms that have been designed for solving complex problems or simple optimization problems. So I want to give a theoretical, say, provide a theoretical framework to understand what is happening, or some aspect of what is happening in deep neural networks. And then I would like to focus on simple devices and try to understand what's going on there, because this will give me the opportunity later to, on the one hand, mention the case of some quantum annealing algorithms, so quantum technology, and see how they can actually become effective. And perhaps more interesting, I can use the results to analyze dynamical aspect of, say, recurrent neural networks, which are models that are typical for computational neuroscience and neuromorphic devices. And maybe we have been overlooking some aspect of this system that can allow the design of more advanced type of neural network that may have good learning performance. Okay, so this is the general idea. So let me just start by mentioning some very well-known facts, but still it's worth remembering them. First of all, it's very difficult to, in general, it's very difficult to design models that are at the same time of interest for AI and for, say, neural computation in the biological or neuromorphic sense. Let me just start by just reminding you that our brain consumes very little. I mean, we consume about 20 watts per hour, watt hours, and which is a little amount of energy. And as opposed to this, we have to think that, let's say, ChatGPT consumes order of magnitude more. Even if we consider the total population of the planet, say, the amount of energy we invest in making our brain function, it's not so far from the energy that ChatGPT alone consumes every day. So, but at the level of the single device, of course, there's a huge difference, and therefore the underlying principles are indeed quite different. And this is probably one of the main reasons why the models are so far and difficult to compare. Okay, so let me just mention a few very well-known facts about current technology. We all know that the amount of energy consumed in using at inference time or in training AI system is sizable, in the sense that it's a percentage of the total energy consumed in the planet. And so there's been a lot of work trying to reduce this energy. So there's been work in trying to improve algorithmic efficiency, like by using low precision, model quantization, sparse networks, and things like this, by developing optimized hardware, so efficient GPUs. Even DeepSeek recently has shown how to perform learning by sparing a lot of energy and a lot of compute. One idea which is quite representative of the fact that indeed we need a lot of energy for this AI system is the idea of using renewable energy sources for data centers, or even nuclear power plants for data centers. Then, of course, there's model optimization, in particular distillation. So going from a huge model to a smaller model with similar performance to reduce cost. But all these solutions are actually interesting. They produce results, but they, as far as I understand, they do not represent a structural solution to the problem. So the amount of data and the usage of these devices is so huge that it's difficult to imagine a real reduction of consumption. Also, for edge computing, I mean, we possibly need to rely on data centers, which are very expensive, and so still we are far from seeing a solution. On the other hand, if you consider so-called neuromorphic computing, so kind of a technology that mimics computational neuroscience models, they are very interesting from the energetic point of view. They consume little energy. They are perfect for edge computing, so computing on the devices. However, there's a lot of difficulties that need to be overcome. In particular, they don't scale properly. I mean, you cannot really imagine to use these kind of devices and on applications in which current AI is effective. So the benchmarking doesn't work. So scaling the system is very difficult, and also learning is not as efficient and effective as it would be needed to obtain and to use these kind of devices for real computations. Okay, neuromorphic computing is made of models that are typically recurrent. They are inspired by biological system, and they are few things that are very interesting, namely the fact that they are intrinsically parallel, they are asynchronous. And so in this respect, they could really represent a technological improvement. There are attempts to build this kind of devices. I'm not a real expert in this, but I just want to mention them. So there are some specific chips that you can use. There are models of spiking neural networks that, again, are very efficient from the energetic perspective. There are memory store-based systems and other technologies that are used. Still, we have the problem of making these systems scale and make them really efficient for generic computation. So what is the main difficulties that we encounter? Well, the main difficulty, I would say, is the limitation we encounter during training. Typically, for instance, for spiking neural network, you use spike time-independent plasticity for so-called spike time-dependent plasticity for the weights. But it's very difficult to tune these systems and to obtain, competitive results. So they are good for very specialized tasks, but not really a solution for generic AI computations. So I will try to argue at a certain point that maybe there's something we can do, say, in this direction. I want also to mention, again, this is just a generic introduction that, and I'm sorry if I leave a lot of topics aside, but it's just for the sake of time. There's another field called reservoir computing, which is used to essentially learn and fit signals, and which is, again, based on recurrent neural networks. You have, say, an input layer, a recurrent neural network that implements a certain type of dynamics, and then you have an output layer that can be trained. And now with this kind of system, you can actually say mimic signals, okay, learn signals, but again, these are not really used for AI application due essentially to the fact that the recurrent neural network is fixed, and so it has some kind of limited possibility in terms of learning complex sequential tasks. Okay, so now, so what I've said up to now was just a generic, say, introduction to clarify the fact that there is a big problem, and there's a lot of interest in trying to develop systems that are at the same time competitive in terms of AI performance and sustainable from the energetic and technological, say, perspective. This has a lot of consequences also in society, in the sense that one of the drawbacks of modern AI is that it is in general very expensive to develop. So it's kind of also important in this respect. So now I would like to enter in the technical part of this presentation, in the sense that I would like to share with you some results concerning some basic facts that take place during learning in deep neural networks. I consider deep neural network as like a multi-layer network, like the one represented here as the prototypical model. So I would like to discuss what happens in the so-called learning landscape, and how is it possible that simple algorithm work, and see if this can lead to new type of models and insight. So let's just to fix the idea, we are going to consider, say, a neural network, which is performs a nonlinear transformation from input to output. And so the output is typically given as the argmax of the output units, and the network implements, a series of nonlinear transformation, and the parameters of the models are, of course, the weights of the network. I mean, convolutional network, transformers, and even diffusion model, but behind have this type of structure. Okay, so how do we train this system? Well, the idea is very simple. The idea is that we can define a cost function, let's say for a classification problem, that just counts how many error we make on the examples that we provide to the system. And this is called the 0, 1 or number of errors loss function, so which is just equal to the number of errors. So it's a discrete function, which, however, is not differentiable, so it's not really used in for learning. What is used are some surrogate loss functions, like, say, the mean square error, or more common, the so-called cross entropy, so the softmax, essentially, loss function, and which have the characteristic of upper bounding the 0, 1 loss function, and therefore optimizing them is, also kind of bounds the error loss function. And the advantage of this loss function is that they are differentiable, and so we can apply all the machinery that we are now familiar with. Now, okay, and at this point, you have all the techniques that, like stochastic gradient, backpropagation, all regularization techniques, all the things that we have been learning in the last decade. Now, one question that I would like to discuss with you is the fact that these are very highly nonlinear devices, and in principle, these loss functions have a lot of critical points: local minima, saddles, absolute minima, narrow minima, wide minima, and so on and so forth. So let me give you just mention to you some recent results in theoretical computer science that can be of interest in this field, to understand how is it possible that the algorithms kind of do not get trapped and are able to find a solution. So the result that I would like to mention to you is called the so-called overlap gap property. And this is a result that was developed, let me say, in statistical physics of disordered system, but has been put on, say, rigorous grounds by many mathematicians. And I would like to refer to the work of David Gamarnik in this particular talk. So what is the idea? Well, on the left, you see a picture of what I imagine to be the set of zero error configuration of the weights for a given, say, loss function. So you can imagine to have, regions, so-called modes in the energy landscape that can be connected, that correspond to the fact that the loss function is minimum on those spots. And so you can see you can have kind of isolated regions, you can have wide regions, or you can have very wide regions. Now, the overlap gap property states the following results: that if this solution, this minima, let me call them minima, are isolated, namely the fact that, well, you have to bear in mind that we are in a very high dimensional space, so everything is not as intuitive as it looks like in 2 dimensions. But if the minima exhibit a gap structure, namely that they are isolated, so around the solution you have a minimum, and therefore around this solution you have no other minima, then, and if this is true for all the minima, then a huge class of algorithms are going to fail. In particular, the theorem, the informal statement of the theorem goes as follows: if you have a combinatorial optimization problem that exhibit this property of having isolated minima, and learning is an optimization problem. So you can imagine that each pattern you want to store in the network is nothing but a constraint that you want to satisfy. Then if a stable algorithm is applied to solve the problem, then it will fail in finding solution with high probability. So this is a kind of interesting result, because it tells you that the situation in deep learning cannot be of the type we are seeing on the right of this picture. So solution cannot be isolated, even though they exist, these narrow solutions, but this narrow solution cannot be found by stable algorithm, which is a huge class of algorithms. I'll come to it in a minute. Okay, so this is the generic situation. And so essentially in practice, what this means is the following. Imagine that in this picture, you have this red curve are the loss landscape as a function of the parameters of the model. This is, of course, just a one-dimensional section. And this picture are taken from Gabarnik's paper. Essentially, what the theorem tells you is that if you have minima that have a size, an internal size, which is smaller than the typical distance between different minima, then these stable algorithms are going to fail, okay? As opposed to the situation you can see here on the right, in which you have multiple minima, which are wide enough. And so the distance between minima is actually smaller than the typical internal size of the minima. One thing that should be said and kept in mind is that if you run your favorite algorithm for training a neural network, you will never observe the narrow minima, okay? Because they are not accessible. So all the empirical measure, all the numerical experiments have to be done keeping in mind that the general shape of the landscape can be quite different from the one that you actually observe numerically. As you know, this is a picture again taken from Gabarnik's paper, in which it tells you the following, that these blobs are nothing but the space of solution, or the minima of some cost function is the zero error section, say. And what happens is that if the minima are connected somehow, then they are you can actually find them using stable algorithms. And this, by the way, probably for those of you who have been following the literature in deep learning, probably read something about mode connectivity. So it's quite well known that minima in deep networks are connected somehow. And so what the theorem tells you is that if that is the situation, then the algorithm are going to succeed, whereas when they become disconnected, the algorithms are bound to fail. Here on the horizontal axis, you have essentially the number of constraints of your optimization problem. Let me say that the size of the training set. Okay, so this is the situation. Still, sampling the isolated minima still remains impossible. So again, what I told you before should be kept in mind, that what you observe by numerical simulation is just the connected part of the overall geometrical structure. Now, but the question is, which are the algorithms that are bound to fail? Well, these are the so-called stable algorithms, which essentially can be thought of as kind of smooth algorithms, such that if you make a tiny change in the input, you have a tiny change in the output. But what is relevant for our discussion is that gradient descent is one of these type of algorithms, and therefore this picture applies to learning, okay? So having said this, let me turn to the simplest non-convex model, which is the building block of all neural networks and all the AI system, which is the single neuron. And here I'm going to consider the case in which the weights are binary. So not continuous weight, but binary weights. Why do I do this? Just to keep the model as simple as possible. In order to observe the phenomena that I just described to you with continuous weight, I should have a slightly more complicated architecture with one hidden layer or so, which just makes things more complicated. So I prefer to focus on this device and see, by analyzing this device, which are the results and how they can lead to algorithmic insight and hopefully to new models. So now this is the simplest neuron. So in the input, you give a vector x, and you want to read in output a given label y, so a given classification of the pattern. And so let's imagine for the moment, for the sake of analysis, that we have random inputs and corresponding labels. And we want to see what happens as the number of patterns that this network is required to learn increases. So we define a control parameter, which is the ratio between the number of patterns and the number of weights. Now, as I said, these results generalize to networks with continuous weight, but I think it's enough to analyze this simple device. And the activation function, we take as an activation function just the sign of the pre-activation. So the neuron sees the sum over j of w xj. This is the pre-activation. It takes the signs and produces a label. And what you want is to find the W such that a given input-output mapping is implemented for all the examples of the training set. Okay, good. Now, if one analyzes these very simple devices, what one finds is a very interesting result. This is no results of the 90s, is that for random pattern, there exists a critical threshold, so a critical number of patterns that this single neuron can store, which is 0.83 times the number of weights. Of course, there is a maximum number of patterns bound for the number of patterns given by information theory, because you are just storing patterns with binary variables, so with bits. And so you cannot store more than n bits, random independent bits with n binary weights. So alpha equal 1 would be an upper bound. But okay, in practice, for random patterns, you find that there is a critical threshold beyond which this system cannot store any more patterns. But what is interesting is the following, is that if you look at the structure of solutions, it turns out that if you just look at those that are most numerous, you find that they're all isolated. So this is a computation that can be done using theoretical physics tools, and then have been proven to be true rigorously also by mathematicians more recently. But what happens is that, in fact, they are all isolated. So based on the OGP theorem, one would tend to say that the overlap gap property theorem, like to say that learning is just impossible for this kind of systems. In fact, this is not the case. It is possible. So where is where is the problem? So if one looks at the typical distance between solutions in this kind of device, one finds that it's always extensive. So they are all isolated. Extensive means that the Hamming distance between two configuration of weights that train learn the training set is of order n. It's a fraction of n. So it's a huge distance. So, but we also know that algorithms do find solution for this device. So what is the catch here? The catch is that one should consider also rare events. So it's not very for the overlap gap property. It's not important to consider which are the most numerous type minima. So those that dominate the probability measure, say. But it's important to look at rare events. Algorithms that work do not necessarily are not bound to find the most numerous one exemplar of the most numerous minima. On the contrary, they can find kind of rare minima as far as they are accessible. And this is exactly what happens here. So what we did some time ago was to try to think about this problem, and because the situation could be that a bit like the one represented in this picture, in which you have a lot of minima that correspond to perfect learning, like the green minima in this picture, and at the same time you have some rare region in which you have you can find a flat, wide region containing many minima. It's a bit like having a golf course with an exponential number of holes, but somewhere you have a lake that is very difficult to find, but this lake is big and contains a lot of solution. Okay, so the way we analyzed this problem was by introducing what we call the local entropy. Simply, instead of trying to minimize the loss function, we said, well, let's try to look for regions in the weight space that contains a lot of solution. So instead of just looking for a point-wise solution, we look for a hypersphere. We move around the space of weights with the hyperspheres of large radius, and try to find the regions that contain a lot of solution inside. Okay, so what we define is sorry for this technicality, but then I will give it up. The idea is that what we are going to optimize is not only the number of errors, but also the density of errors around a reference solution. This is our objective function. So we are not going to consider the usual loss function. We consider a loss function which tries to find the regions that contain a lot of solutions around inside extensive regions. This can be rare, but they could exist. And so in order to do this, we define what is called the local entropy, namely just the number of such solution, the log of the number, because this number is normally exponential in number of parameters of the model. And so in this way, we define a new function to optimize. And we can have a hard version or a smooth version, which we introduce a temperature, but this is not very important. And we call this quantity the local entropy. So the entropy contained within a hypersphere, a ball of radius d in high dimension. And if you do this, so it's a bit like saying, instead of looking to the landscape through just point by point, we look through a lens that allows us to explore entire regions of extensive diameter. So the idea is that if this is the landscape we are dealing with, the loss landscape we should optimize, over which we should find the minima for learning, what the local entropies does is to smooth out this landscape and just to focus on the wide minima. Okay, so we are trying to solve the red problem and not the black problem, which is the original one. Now, if you do this, you discover that in the binary perceptron, for instance, the simplest non-convex device that I was mentioning to you, indeed, there exists this dense region that were not expected. And this clarifies why the algorithm will work, because there can actually, there's no theorem telling you that you cannot access these regions. And in fact, as a matter of fact, this is where the algorithm end up. Okay, so something that I haven't said before is that, of course, say, before deep learning, we were mainly concerned with optimizing machine learning devices that were convex, like, say, supervector machines and so on. So we didn't have this type of problems. But with the advent of deep learning, of course, the non-convex nature of the optimization problem has become central. Okay, so without entering into the, say, details of these pictures, just to say that if you look at these dense regions, they appear and they exist. These regions are just a region composed of many very stable high margin solutions. So also they lead to good generalization performance. So given that I see that the time is not much, I'm going to skip all these technical aspects. And so somehow you have to imagine that the deep networks have, I mean, this non-convex network have a space of solution which is composed of many point-like solutions plus disconnected regions that are very dense in solutions. And there's been also rigorous proofs of this recently using probability theory and not only theoretical physics results. But there's an obvious algorithmic check that one can do and simply perform a kind of a simulated annealing or Monte Carlo search for solution using as a loss function not the loss, say the mean square error or the cross entropy, but directly the local entropy, which can be approximated by certain techniques, and one can find that indeed it is effective. So everything seems to be nice and confirmed. Now, one very interesting follow-up of this result is the fact that you can show that an equivalent formulation of this local entropy approach is to just consider multiple models. And so instead of just optimizing one single network, you take Y replicas of the original system and you impose a distance constraint between this system, these replicas, and you can show that the barycenter of this replica is actually going to end up in this wide minima. So sampling from a replicated system focuses on the dense rare regions of the neural network. So this is very useful, and a lot of algorithms have been developed. And so you can think of, a strategy for optimizing this learning is to consider many replicas and look at the barycenter, okay, with the distance constraint. I know that this is very theoretical, but I will come to the practical results. Okay, the first practical result that I want to mention is that if one looks mathematically at what happens, it turns out that this idea of replicated is present also in quantum computing, because if you consider what is called quantum annealing, that is the idea of taking your classical optimization problem, which could be, for instance, a learning problem. What you can do is to add a transverse quantum field, initialize your system in the direction of this transverse field, and then reduce the external field until you reach your optimal solution. This is the quantum annealing, say, approach in few words. And if you do this, in order to do the Monte Carlo simulation of this quantum process, what you have to do is a so-called Suzuki-Trotter transformation. Again, it's not very important, but what is important to observe is that quantum annealing corresponds to the idea of taking many replicas of a single of your problem and coupling them along a chain, like the blue picture here. Whereas what we had before is having a lot of replicas, but coupled to a centroid. Now, the two things are different, but for small distance, they are actually very similar. And so inspired by this, we actually checked that, in fact, quantum annealing works very well for this kind of problem. So just to say that this is a first message to actually be effective in learning in highly non-complex scenarios, because it can take advantage of this local entropy structure of the minima through, for those who are physicists, through delocalization, but that's not very important now. Just to say that this is a first message that this kind of technology could be actually useful. Now, the one thing that I want to just mention to you is that, okay, keep in mind for what I'm going to say briefly, shortly, is that if you take a learning problem and you replicate it, imposing distance constraint, either by a centroid or along a chain, this is going to be kind of an effective way of converging to minima. Now let me go to neuromorphic and computational neuroscience. So I can ask the question, does this kind of geometry also appear in neuroscience or computational neuroscience model, in neuromorphic models? So can we actually use this to build kind of technologies that are more energy efficient? Well, in order to do this, I'm going to consider again the simplest model, and the simplest model is just is just an asymmetric neural network. So I take n neurons, I connect them through recurrent connections, and I want to study which is the space of fixed points. So how can this system converge, or does it have a chaotic behavior, and so on and so forth. So I'm trying to see what happens in the case of this model. So keep in mind that now our objective is we have a dynamical system in which we have, say, S represent the state of neuron I at time t. So we have Si at time t plus 1 equal to some nonlinear function of all the incoming signals from the other neurons. So J is the coupling. Instead of W, I use J here. And as J is the state of a neuron connected to I at a previous time step. And now I'm going to consider the simplest possible model, namely binary neurons, active, non-active, and a totally random network. And what I want to study about this network is how many fixed points you have. And is it possible to converge, and so on? This kind of, so can it work as a computational device based on the fact that it converges? Now, there is a strong similarity with what I told you before, because what I told you before is that if you take a perceptron with binary weights, you have to solve for all the patterns in the training set, the equation sigma mu equal the sine of a sum over I psi I mu wi, namely psi are the patterns, sigma are the labels. Previously I used x and y, but it's again the same thing. And you want to find the w's that satisfy this set of equations. How many equations you have? A number equal to the number of patterns. And we know that there's the maximum number for random pattern is given by 0.83n. There's this critical threshold. Now, in the case of asymmetric neural networks, we want to find mathematically an equivalent problem because we want to find Si equal the sine of a sum over j, 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 s, j, which is of the same type of equation. The difference being that now we have n constraints because this is a fully connected network. So somehow we are above capacity. So what happens for this type of network that in fact, it's impossible to find solutions. We need to simplify the system somehow. And in fact, if one just looks at this system, it's a very well-known result from the 90s that this system behaves in a chaotic manner, just because there are no fixed points present, and therefore the dynamics is bound to never converge. Okay, this you can find the reference there. I don't want to enter in this discussion. So one can relax a bit the constraint by adding, say, a diagonal term, so a self-interaction that makes easier to find fixed points. But again, what is known is that a simple dynamical scheme, a simple update scheme, here you see the equation for continuous time, but these are just the same type of equation you would have here for discrete time. And again, there's 40 years of work on this in which they discuss the chaotic behavior of these systems. Now, what we want to solve is the problem of having study the convergence of the system in which we put a self-interaction JD. Again, this could be mimicked by some other type of interaction that just makes things simpler. Now, okay, let me go to the point because time is running. So what we find is that indeed, as this self-interaction changes, the number of fixed points follows the curve here on the bottom right, namely that as the self-interaction increases, at a certain point, you start to have a lot of fixed points. Okay, and in fact, when the self-interaction goes to infinity, all the configuration becomes stable because you see Si is equal to the sine of JD times Si. If JD is very big, the other term doesn't matter. So all the configuration are actual fixed points if JD is positive. And so, indeed you find a number of fixed points, 1 over n, the log of this number, which is log 2, namely you have 2 to the n such configuration. Now, the interesting point is that by analyzing the local entropy structure is that, in fact, you don't need to go so far with JD. It happens that for intermediate values of the self-couplings, you do have these wide clusters, regions, connected region fixed point that appear. Okay, so this is a first result, which is not yet published, but it's quite clear. And so all of a sudden, convergence becomes possible and, and maybe can be used for computational objectives. Okay, so let me skip some algorithmic consequences, but already for this kind of system, we can show that there are a lot of algorithms that actually would work and so can allow to build a new system. Now, what we can also do is, and this is very interesting, and I'm almost reaching the point I want to reach. So the fixed point that this network reaches can be driven by an external signal. So suppose you have an external signal that couples to all the neurons that forces them to be in a certain direction, say, an external field. And one can show that the dynamics converges to fixed points that have a high overlap. They're very correlated with this external signal, and they are inside this connected region. So somehow one can consider this as a working memory that is capable of associating to each input a certain internal representation. Okay, and here you can find a lot of interesting results about the structure of this internal representation. Now, how to implement learning? Well, in order to do this, let me just mention one fact, and then I will reach the conclusion, that if you now imagine, let me remind you that if you take multiple systems, they tend to converge more easily. They tend to focus on this dense region. So we expect the dynamics to converge more efficiently. And so what we find is that, in fact, if you take many such recurrent networks and you couple them along a chain, then indeed you can have a convergent behavior. And so given this convergent behavior, you can now imagine to use this system just like a neural network, a deep neural network that is able to map inputs to output. Okay, and so you can perform learning and a lot of and all the stuff we are used to implement using deep network. And the way you do perform learning is very different from backpropagation, because now you just need to converge and apply local rules. So this system would represent a system in which you don't need backprop, you don't need this kind of heavy learning tools. You can impose a lot of sparsities. They are totally parallel. Sorry, they are totally parallel, and so now the question is how to benchmark them. But at least we have a platform to perform such benchmark. And by the way, there is an interesting biologically known fact that in recurrent network we have a subset of very strong positive connections that coexist with very small competing synapses, and which essentially might play the same role as this multiple connection, this replicated connection that I've just mentioned to you. So to wrap up, because I'm out of time, what I apologize for being very theoretical or not talking just about models and without, say, actual numbers. I can give you some numbers, but this is work in progress, and I still wanted to share it. The idea is that, in fact, there is a lot to do in the context of recurrent network, neuromorphic, or computational neuroscience models, and we have not been really benchmarking these models with AI, but maybe there is a way out of this, and we should just be more put more effort in doing this. And I think that this preliminary result, together with a lot of other works that I didn't have time to mention, but give a perspective in this direction. And so hopefully we will see models coming up in the next year that are not as expensive as the current transformer systems, because these kind of ideas can be applied to any type of architecture. Okay, I think I'll stop here. I apologize for being theoretical, but it's kind of sometimes nice to have multiple point of views from theoreticians, from applied researchers, and hopefully there's something that we can discuss together. Thank you.
Yeah, thank you very much, Ricardo. And there is a question. The research activity for alternative and energetically sustainable AI systems requires a lot of investment. How can you overcome this?
Yes. So, okay. Yes. So the key point is that these systems that I was trying to describe are fully parallel, and they can also function in a very sparse regime in which just few neurons are active at the same time, which means that they are cost effective. So they could be, first of all, they could be implemented somehow if one could design the connections, and everything is local. It's not like in backpropagation in which you have to propagate the outputs, the error signals throughout the network in a kind of complicated way. This is it's totally local and parallel. And so in this respect, it could lead to very cheap kind of implementation. Of course, a lot of work needs to be done, and a lot of investments also in this work, because now we are totally focused on high performing models, and so that we need probably a shift in a little bit more research in this direction. Yeah.
Okay, thank you. And why researchers in computational neuroscience are not interested in benchmarking their models against current AI systems?
Well, this is so the colleagues working in computational neuroscience are typically interested in trying to understand how specific circuits in the brain works. So they make models and they answer questions that are related to the specific behavior of a given circuit. And they tend to just not care about benchmarking the models for, say, competitive performance with respect to, say, AI systems. Sorry, I continue. And so there's a fracture in the community. So there are fantastic researchers in the field of computational neuroscience that have a great deal of knowledge, but they just don't care about AI, and vice versa. And possibly in between, we are going to find nectars that have a reasonable metabolism, namely they're not as an energy hungry as AI system, and still have a very good performance. So I think there is a fracture in the community, and so there's a niche to be filled.
Okay. And the last question, the so-called world models are more energetically sustainable. Is that correct?
Well, this refers to the future of AI. There's a long discussion about how, say, AI is going to evolve. On the one hand, language models are going to evolve towards, say, higher levels of, let me say, intelligence through some planning and problem-solving capabilities. So we are already seeing this through what is called chain of thoughts. So improved performance. So what happens in current AI is that systems have been growing in size enormously, and the performance have been growing accordingly. Then at a certain point, some signal of saturation appeared, and so what we, in a sense of the community, did was to add some computation at test time to overcome this saturation effect, and so the performance had been growing and growing continuously. So so the scaling has been increasing continuously. Now, there are a big part of the community believes that the systems are going to saturate. They're not going to solve all the problems. So the different models are needed. One candidate is what these kind of models called world models that are kind of advertised a lot by Yann LeCun, but by a lot of other people. And the idea there is that you train this system to learn directly internal representation at the level of internal representation, a higher level compared to the details like tokens, like images that are typically represent the way in which language model perform also planning and so on. And so these are advanced systems that are starting to give some good results. And at the moment, I cannot answer the question whether this will be more energetically efficient, but somehow there is the idea that at the end, if you look at the kind of recurrent systems that are present in computational neuroscience model or neuromorphic model, the understanding of internal representation is crucial, and learning happens at the level of internal representation directly. So maybe there is a connection there. So I cannot answer directly this question, even though I simulated it. But they're quite different from the standard system we are used to, namely transformers and autoregressive models and so on. They are substantially different. So there's room also there for a better sustainability.
Okay. Yeah, thank you so much. These were all the questions, and yeah, looking forward to new discoveries. And thanks again for presenting, Riccardo.
Okay, I hope it was not too theoretical. Okay, bye-bye.
Bye.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good.
you.